Hey, I have an assignment for you guys, but I thought I'd make this little video just to give you a clear idea of what I'm looking for. Linear algebra can be daunting in the sense that achieving some of the objectives can require a lot of very tedious manipulation, and I don't really see the need for that in this day and age. I think we can make this subject a lot more enjoyable. However, I do need for you to show me like your reasoning that you understand um, how you're applying these concepts. So I'm going to show you like what I'm looking for, and then when you do the assignment, you pretty much do the same thing. All right, so let's get started. First, I'd like to briefly review matrix multiplication. Now, here are two matrices, and we're going to multiply them. And you know the basic rule: the number of rows, the number of columns here has to be equal to the number of rows over on this side. And so we've discussed this in depth in class. The way you learn to do matrix multiplication, let's say in high school, is what is called the dot product. Now you say, like, to get this number 64 here, well, it's 8 times 4 plus 4 times 7 plus 2 times 2. And then to get this value here, you say 8 times 8 plus 4 times 9 plus 2 times 6, and so on. Well, there are other ways of looking at this at matrix multiplication. In the end, they're all the same. So whenever you're carrying out this process, no matter how you look at it, you're still in a sense doing those dot products, as you see right now. However, it is helpful to look at this thing slightly from different points of view, from slightly different points of view. So what I want us to do here, and again, this is not the only way, but I want us to, for this discussion today, look at this way of multiplying matrices. What I want to do is get this row, not just this value now, I want to get this row by finding a linear combination of these rows. And what are the scalars involved in that linear combination? Well, it will be these values. So 8 times this row plus 4 times this row plus 2 times this row will give me this row. Right? Again, the linear combination of these rows give me this row. However, this time it's the scalar values from this row that will determine. So the scalar values of this row determines this row, the scalar values of this row determines this row, the scalar values of this row determines this row. So it's going to, so this row here will be 5 times this row plus 6 times this row plus 3 times this row. This row will be 7 times this row, 2 times this row, plus 9 times this row. So I don't know if I've been saying that plus. So just make sure, for example, this row, it's 4 times this row plus 6 times this row plus 3 times this row. Of course, if we looked at that deeply, it's the same dot products, For example, if I did this row times this row, 8 times this row plus 4 times this row plus 2 times this row. When I actually come down to doing that, I'm going to have to go, for example, to get this value here, I'm going to have to go, well, it's 8 from this row, so it's 8 times 4 plus 4 times 7 plus 2 times 2. Notice it comes back to the same thing. But it helps to see this in this way. It's like a faster view of what's going on. And it also helps you, like, if you're going to program these things, if you want to use, say, Excel to kind of speed up the process. All right, so let's, I hope that makes some sense, right? And we'll take a look now at how, at a case where it becomes very clear now how it's nice to look at things this way. So let's look at this example of a very simple multiplication. We have an identity matrix here, and we're going to multiply this identity matrix by this matrix, and of course we expect to get back this very same matrix here. Now, with this way of looking at the way I just described, now of looking at the matrix multiplication, it becomes very clear, right? Because now when we do this multiplication here, well, it's 1 of this row plus none of this row plus none of this row. It's none of this row plus this row plus none of this row. And here it's none of this row plus none of this row plus this row. So that should be very easy to see now. So let's see how we can apply this idea to the process of taking our matrix to echelon form. And then later on we'll see how we can take it all the way to reduced row echelon form. Well, the first thing I'd like to do is get zeros here. So how can I get zeros here? Well, I simply replace this row with the result of what? Taking this row and subtracting 6/4 of this row from it. Likewise, I can get a 0 here by taking this row, by replacing this row with the result of subtracting 9/4 of this row from this row, right? And so how do we write that out in a matrix? Starting from this one here. Well, I will write 1, 0, 0 here, and then I'm going to write minus 6/4, 1, 0, and here I'm going to write minus 9/4, 0, 1. And I'm going to multiply that by this matrix here, right? So I'm having a little difficulty controlling my little pen here. And so over here, well, it's one of this row plus none of these rows. So that's going to give us 487. And then it's minus 6/4 of this row. So let's do that. So let's do it. It's minus 6/4 of this row plus this row, right? In other words, it's this row minus 6/4 of that row. So let's take a look at that. If I do minus 6/4 times 4, and then I add that to 6, notice I get 0, which was what I intended to do, no? And then if I come here and I say, well, notice it's minus 6/4 of 8 plus 11. So it's minus 6/4 times 8 plus 11. And that gives me minus 1. So minus 6/4 times 8 plus 11 is equal to minus 1. So I hope I'm not making any little errors here, right? If I am, please tell me about it, no? And then here it's minus 6/4 times 7. 7 plus 14. And we get 7/2. Notice? And then here, it's now going to be minus 9/4 of this row plus this row. In other words, this row minus 9/4 of that row. So I'm just checking to make sure it's correct, right? So I'm going to multiply minus 9/4 times 4 and add it to 9, and I should get 0. And then what I want to do here is then say minus 9/4 times 8 and add it to 2. Right, so it's minus 9/4 of this row plus this row, right? So minus 9/4 of 8 plus 2, that gives me minus 16. And then I want minus 9/4 of 7. Plus 5. Minus 9/4 times 7 plus 5, and that gives me minus 43/4. And let's clear this up a little bit here. Alright, so that's still not too clear. Minus 43/4. All right. So what I'll do in the next when I come back is show you how we could have done this a little bit quicker. So you should practice this a little bit, no? But in the end, we have software that can do that, and so let's not make our life too tedious. No? So I'll show you. There's this nice website called Symbolab. If you have some other that you prefer, go ahead. No, so let's do that. As you can imagine, having to do this for large matrices would not be fun at all. It's so very easy to make a mistake here, and so in actual fact, this is the kind of job that is perfectly suited for computers. And luckily, we live in a very computerized age. So let's go over to Symbolab and see then how we could check this. Now, there's a lot that computers can do for you, and obviously I'm not going to accept your work if you just show me an answer and well, you just had a computer do everything, because then, well, that's not going to be acceptable. I need to see at least I need to see some intermediate stages. So for example, if you had to carry out the take this to a reduced row echelon form, I want to see what I'm looking for is for these elementary matrices, right? So this is an elementary matrix, right? It's going to carry out some transformation of this matrix here, taking it hopefully closer and closer to reduced row echelon form. And so what I'm looking for is that you can look and see which elementary matrix you need, right? And then you can always have some application carry out this process for you, and then you see what the result is. And then you're going to apply another elementary matrix to this one, and so on and so forth until you are completed. That's pretty much what I want to do. So let's take a look at Symbolab. So here we are at Symbolab. So you're not seeing the whole screen, so let me see if I can maybe reduce this a bit or something. And so if I were to bring this in, see that's Symbolab, and alright, so we don't need to see all of that though, right? So I think right here is enough, right? I have a little square on my screen that shows me what you should be seeing. So you can click right here for our matrices, and then I can say, well, I want I'm going to multiply two 3 by 3s, right? So I'll just put 1 here, and this will have what? 1. I'm just pressing tab to go to the next cell. 1 0 0. Then I come here minus 6/4, and then here 1 0, and then it's minus 9/4, and oh, I didn't put the 4, and 0, and then 1. So that was my elementary matrix. And then I'm going to place my... By the way, if you need to work with a matrix of a different size, then you can just pick the size of matrix that you want. So it's not infinite, no, but this is up to 10 by 10. That should be more than enough for anything you may need. If you need to work with matrices bigger than that, then you need more professional software now, or work with, say, programming languages like Python. All right, so let's do the next one. 3 by 3, and this was our matrix now that we wanted to transform, and that was 6 11 14 9 2 5. Right, and so this is how I check my work, because it's so easy to make a mistake with this. Now, so let's just check. It's 1 0 0 minus 6/4, 1 0 and minus 9/4, 0 1, and here we have 4 8 7 6 7 14 9 2 5, and let's see if I did this without making a mistake. And so here is our answer: 4 8 7 0 minus 1 7/2, 0 16. I got 1/6. Maybe I didn't look at my calculator good enough, so... Oh, it's minus 16. I don't know why I thought I got minus a 6. I think when I copied it down, I have a piece of paper here that I'm working with, and keeping track of what I do now, and I wrote down minus 1/6. So I was correct then, and let's see, is it minus 43/4? Let's look again. And yes, minus 43/4. So it's 4 7 0 minus 1 7/2, 0 minus 16, and minus 43/4. So again, right? You should be able then to carry out this process then. So what I need you to do when you do your assignment is come up with the elementary matrix and then apply it and get the result, and then come up with another elementary matrix, and you keep on doing that process until the process is complete. And so then I want to see those elementary matrices. I really don't see what's begin by having you then manually do each one. Just make sure you understand and that you can do a few. I will try and find a way to test that you understand that. Let's apply what we've just discussed to this problem. Let's suppose you have a system of equations and you're asked to solve it. And so what you do is you create the corresponding matrix equation. And so you have your matrix here, and then you have this vector which will represent your solution. And of course then you're looking for what vector here will give us this solution, no? Such that this matrix times this vector gives us this one. And so what we're going to do is then take this matrix to, we create our augmented matrix, and then we're going to take this augmented matrix to reduce row echelon form. And so we're going to do so using our elementary matrices. So if you look at this, it becomes quite simple. Now what do we need to do? We need to replace, we need zeros here, so we need to replace this row with what? This row minus 6/5 of this row. And we need to replace this row with this row minus 2/5 of this row. And so you look at your elementary matrix here, it should be very easy for you to see now that this matrix does that, right? Because in our resulting matrix, this row will be 1 times this row plus none of these rows. This row will be minus 6/5 of this row plus this row, and this row will be ignored. And this result here, this row here, will be minus 2/5 times this row plus 0 of this row, and now plus this row. In other words, you're going to get this row being replaced by it minus 2/5 of this row. Now, it would be a lot of work if you had to go and do this even with your calculator. So go over to Symbolab like I showed you just now. Type in this. It's still a little bit of work, but nothing near what it would have been otherwise, right? So you would not want to have to do this like when I went to school. No? So you put this in, and Symbolab will give you your answer here, right? And then the next step will be then to transform this again, so we get what? A 0 here, right? Now we want to get a 0 here. So obviously what we need to do then is take 19/28 of this and subtract it from this, right? And then replace this with the result, which of course will be 0, right? So 19/28 times this will give me minus 19/5 plus 19/5, and that will result in 0, which is what we want. All right, so that's what this matrix does here, right? And notice it's going to take this row here is going to be 1 of this row plus none of the other rows. This row will be, well, none of that row, this row, and then none of this row, right? And so then these two remain the same, and this row will be what? None of that row, 19/28 of this row plus this row, and so we get this here. So what you need to do is just think carefully about making these elementary matrices, right? You should think about this carefully and make sure you understand how you're building these. And then you simply put this into Symbolab. Again, every time you do it, unless you can find some other way, you probably have to type all these values in. I would recommend just erasing every time and doing the whole thing over. It's easy to make a mistake when you try to like reuse one, no? But if you can find some way that works for you, well, fine. All right, so that's that. And so when we do this, we notice we have this in echelon form now, right? And well, the next step now is to get ones here, right? So we want the pivots to be ones, and so that's just a matter of multiplying each row, by the appropriate value. All right, so let's do that. By the way, let me just go over the numbers here to make sure that this is minus 20/5, this is minus 17/5, this is minus 3 over 5, this is minus 19 over 5, that's 0, 0, minus 31 over 28, 207 over 28, and minus 33 over 28. So what's left to do? We need to get 1s in these pivot positions, and we need to get 0s up here and a 0 here. So let's do that. To get 1s here, all we need to do is multiply our matrix, this one here, by this one, right? And let's get the understanding of this. It's 1/5 of this row plus none of these rows will give me this row. So I get a 1 here. This row will result from what? Taking none of this row minus 5 over 28 of this row, and that's it. And then you get a 1 here. And likewise here, you take none of these two rows and then minus 28 over 31 of this row. Note, minus 28 over 31 times this will give me a 1. And so what I do then is just, again, I use symbol lab, and I put these matrices in, and I get this result. And so now I have this result here, and then I sit and I think, okay, I need to get zeros here, you know. So where you have the pivots, there should be just the number 1 and zeros above and below. And so now how can I get zeros here? Well, I need to use this elementary matrix here. So notice what this is going to do. It's going to take, when we multiply this matrix by this one, well, this row will simply be 0 of this row plus 0 of this row plus this row here. This row will be what? 0 of this row, and then this row minus 17 over 28 of this row, right? And of course, if we take this row and minus 17 over 28 of this row, we'll get a 0 right here, right? Which is what we want. And if we take this row and minus 7 over 5 of this row, notice we're going to get a 0. So notice there's a 7/5 here, right? We're going to get a 0 here. And so these two values then will be replaced by zeros. Of course, this would be a lot of work if you wanted to do this all manually using a calculator. So again, we use the application, and I see I get my result correct. And then what's the last thing I need to do? I need to get a 0 here. And so again, I create my elementary matrix, and notice now it's going to be, well, these two rows won't be affected, only this one. And so then it's going to be this row minus 8 over 5 of this row, right? And of course then that will give me a 0 right here. And we're done, right? We have now gotten our matrix into reduced row echelon form. We have our elementary matrices, and that was our primary objective. Let's take a little deeper look at this, however. Notice we started with this matrix here, and we applied this elementary matrix, and then we applied this one to the result of the previous transformation, and so on. We could look at those applications like this. This is our original matrix, and we applied this transformation, and then to the result of this we applied this, to the result of all that we applied this, to the result of all this we applied this one, and to the result of all of that finally we applied this. So notice then what we have here then is a multiplication of these matrices, but note how we have them written. It's the last one, then E5, E4, E3, E2, E1. Why? Because this is the first one that was applied. So you need to make sure you are aware of this, right? So matrix multiplication is not commutative, but it is associative. So instead of multiplying this by this first, we could multiply all of these first, right? Which is what I have here, right? And so, and then multiply that result by this to then get what we have here. So let's take a look at that. Now this is not something you would normally do. We're just doing this as an exercise. So if I take all of these, I can multiply these easily by just placing them in say, symbol lab and getting this product. What this means then is that instead of multiplying the matrix one by one, first we apply this and then we apply this to the result and so on, we could simply take the product of these matrices, which is this, and now multiply these two. In other words, this single matrix encapsulates all the steps that we took here. And of course, if I multiply this by this, I will get this very same answer here. So I just did it here in Symbolab so that you can see. And note we get the same answer. Now let's look at what we originally set out to do. We wanted to find this vector here. So let's just do that since we already have our system in reduced echelon form. First thing we notice is that this is consistent, right? We have a solution here. So let's just start looking for it. So we have that x1 is equal to minus 102 over 31 times x4 plus 8 over 31. I apologize for those dogs. That's the way this neighborhood is. So you can see that here from the solution, right? So remember these columns correspond with the variables, so x1, x2, x3, x4. So x1 plus 102 over 31 x2 is equal to 8 over 31. So a very simple algebra, we get x1 then is equal to this, we get x2 is equal to this, and x3 is equal to this. So this means that our vector x, because remember this is, we could just call this x, no? In other words, ax plus b. This vector x then is going to be, or vector x is going to be this, right? And so we have an infinite number of solutions, as you could have seen, because we have a free variable here. x4 is a free variable. All right, so what are the solutions to the system then? Any vector that fits this, no? So it's this vector here, 8 over 31, 1 over 31, 33 over 31, 0 plus any scalar times this. So of course one solution then would be when x4 is 0, and this would be one solution. We could make x4 any number, right? Any real number, and that would give us then other solutions. So I hope you begin to see now how powerful linear algebra is, right? And we are really going deeply now into how we can solve huge systems, right? Okay, so I think that brings us to the end of this little discussion, and so I hope this helps with the assignment. So when I post the assignment, what I'll be looking for, I'll give you pretty much a system like this, and ask you to find these elementary matrices, and then find the combined elementary matrix, the single elementary matrix that encapsulates all of these, and then the general solution. Okay, so I'll just say bye and see you later. Sayonara.